Okay, hello everyone. What I'd like to talk about today is how we can go about selecting the types of physics we're simulating. So you can simulate many different types of physics inside of STAR-CCM Plus. We talked about some of the theory of these in lecture, but the way we do this, let me turn on the mouse highlight. There we go. Is let me get that out of the way. There we go. Is with this Continua folder. Continua is where we define what equations it is using. We define what physics are being modeled. So, if we want to define a type of physics, sometimes if you go far enough in a simulation without making one, it will make one a empty physics continua for you. But if it hasn't yet, you can go to Continua, right-click, hit New, Physics Continua, and it will create a node called Physics. Insert number here. It might be Physics 1 if you have more than one. It might be Physics 2, 3, 4, etc. You can have more than one of these. So, the way we select physics is once we have this Physics 1 node, it makes a folder that says models. We could either right click on Physics 1 or right click on this folder and say select models. This lets us pick what physics we want to simulate. So, generally, the way I do this is I select top down. You can start with any of these that you want, but you pick the space, the type of dimensional space you're modeling, whether it's 2D, 3D, shell, three-dimensional, or axisymmetric. You pick the time modeling, whether the flow is unsteady in different forms, steady, or has a harmonic oscillation to it. You pick what type of material these physics are modeling. Is it modeling a gas, a liquid, a solid, multi-component gases, multi-component liquids, multi-component solids, or is it multiple phases and transitions between one phase to another? Liquid to gas, gas to liquids, liquid to solid, etc. So we're going to select gas for the moment here for demonstration purposes. We're also going to select two-dimensional, steady flow. So this is a fairly basic simulation so far. Two-dimensional, we're dealing with a gas, it's steady. Now, one of the more complicated things that to conceptualize is whether we want segregated flow versus coupled flow. This changes pretty drastically under the hood how it needs to solve these equations. So segregated flow is better for lower energy flows. Coupled flow is good for supersonic or just generally very high energy flows. We are going to stick with segregated flow for most of these, so I'm going to select that now. Now, if we have a simulation where density is constant, and we know that's the case, we can select constant density. Or if we expect density to vary according to the ideal gas law, we can select ideal gas. We can select polynomial density if it's going to vary with something that's not the ideal gas law. Or we could tell it's a real gas or some other fancy equation that we use to define how this gas interacts or how it behaves, the equation of state for this gas. Usually you won't have to do anything other than ideal gas or constant density, but if you start breaking the assumptions that go with either of these, you might need to use fancier equations to define how the gas behaves. So we're going to stick with ideal gas for the moment. So we have a couple different ways we can treat energy in a segregated flow modeled gas. We can have it calculate enthalpy. We can have it treat the gas as isothermal, that is, the temperature is the same everywhere, or we can have it calculate temperature. Usually, if we're going down this route, segregated fluid temperature is probably the best one. And with most flows, there's probably going to be some meaningful amount of turbulence, so you're usually going to want to select turbulence in some form. Here, we talked about selecting these different turbulence models in class, in lecture. However, to give you the Cliff Notes version of this again, K epsilon is a two equation model of turbulence. It doesn't calculate turbulence directly, it just predicts the effects of turbulence. K epsilon is great if you know there's going to be flow separation, but you really don't care about the specifics. Either it's really obvious where it's going to separate, or you don't care where it separates for whatever reason. But you know that there is probably going to be flow separation. K omega is going to predict flow separation more accurately, where it happens. It's not going to be perfectly accurate, but it's going to be more accurate, and is good for applications where you expect flow separation and the location of that flow separation is going to significantly affect the model in question. Reynolds stress turbulence is a slightly more advanced form than either of these. Will give you somewhat more definition, but more computational expense. Spolart Almaraz, if I'm pronouncing that correctly, is a one equation model for turbulence, not two. K epsilon and K omega are both two equation models. This one is one equation. This is best for applications where you do not expect flow separation. Smooth attached flow over an airfoil, for example. You're unlikely to get flow separation. That would be an excellent use of this particular turbulence model. So which turbulence model you select? Again, we've gone into more depth in this at this point. However, what type of problem you're looking at is going to define which one of these you're selecting. Are you actually dealing with an ideal gas, or is it effectively just constant density? Is it steady? Is it actually two-dimensional, or do you need to account for all three dimensions? What you're looking at in your problem, what the general type of flow you expect to see, is going to define how you select these models. For today, we're going to select K omega. We have some optional features for how it predicts the transition between laminar and turbulent flow. We're not going to select them for today. We may go over them later, time permitting. And down here we have a whole bunch of optional models. These do many different things. I'm not going to go through all of them, but there are a couple that may be important. The first one that's most likely to show up is gravity. If you have buoyancy effects due to flow, heating, or cooling, buoyancy effects can matter. If you have flow that is tangibly or significantly moving against gravity in reality, you might want to account, or with gravity, you might want to account for the effect of gravity on that flow. It is a body force, which can affect the flow if it's doing significant vertical changes in the direction of gravity, or in the anti-direction of gravity, that is up or down. So gravity can matter significantly in some situations. So we'll select gravity for the moment. The other two that might come up is in more advanced subjects. We're not going to go into the details of these, but you should know they're there. Is porous media. Porous media is if you want to model flow through, for example, a filter. Something that's porous, it'll let flow through it, but it has significant resistance to it. Or heat exchangers, radiators, or other closely packed surfaces where you really do not want to explicitly model the flow as it moves between the individual fibers or fins in a filter or heat exchanger. But you know those things provide resistance to flow. Porous media. Actually, no, not porous media. Sorry. No, you don't need porous media for this. Porous media is really if you have like a packed particle filter or chemical reactor or something like that. Porous regions, which is what I was starting to describe, is something different, and I apologize for any confusion. Porous media is really if you have closely packed particles of sort of irregular size or semi-regular size, but you want to model how and figure out how flow moves between those particles. We definitely won't need porous media for this class. We might talk about porous regions, which have a similar name, but are something different. I apologize for any confusion. Radiation deals principally with heat transfer and heat transfer via radiation. Pretty self-explanatory. Usually, heat is only transferred via conduct, or significantly is mostly transferred via conduction and convection. If radiation is the significant mechanism of heat transfer, you might need to use this model. And it'll account for the paths that heat can take radiatively through a system to some extent. We don't need that one for today. So the other thing to note here is that while we selected some of these, we told it gas, two-dimensional, steady, segregated flow. It selected some of these on its own. Gradients, it selected automatically because it needs gradients for segregated flow. When we selected turbulent, specifically, we selected, I believe, K omega turbulence. It selected Reynolds averaged Navier-Stokes as what it uses kind of as an under the hood basis to build the K omega turbulence model. These various other things, it selected automatically. All Y plus wall treatment we talked about in class. Wall distance we talked about in class. And it's using these to model turbulence. Usually, if it automatically selects something, it's probably right. Unless you have a very good reason to override it, I recommend leaving those alone. There do exist reasons to override its selections. We probably won't get to any scenarios in this class where that applies. So once you have all of your models selected, you can just hit close. They remain selected, and if we look in the tree on the left here, we can see that under this folder, it shows us all of these models. We'll also note that we can tell it what gas we want to use under this gas node. If we want to change the gas that we're using, we can go under this gas node and select or right-click on the gas it's selected, which by default it will always use air, and we can say replace with. It has a database of gases, some of them quite exotic, that you can select from. Some standouts on here include hydrogen cyanide gas. We have isooctane, some hydrocarbon form. Sulfur hexafluoride, sulfur dioxide, carbon tetrafluoride. That's probably a particularly nasty one. Let's see here. What else do we have? We have aluminum gas. I probably don't want to be around that one personally, but you have a selection of gases you can choose from that it will have physics properties in their database for how these gases behave. We're going to leave it on air for the moment. We don't need to do anything exotic today. But for these different gases, you'll have different properties depending on what physics you've selected. You'll have things like specific heat, molecular weight, dynamic viscosity. Note, dynamic viscosity could be a constant, or you could change it. So let's see here. For any of these, or not any of these, for a lot of these, by default, it'll just assume a constant value that's approximately correct for everyday conditions. That may or may not actually be the case. So, for example, if dynamic viscosity isn't about 1.85, or you expect it to change significantly over your simulation, maybe you have large changes in temperature. you can change. So let me back up a second. So under material properties for air, instead of telling it, hey, this is a constant dynamic viscosity, you can tell it, I want you to use Sutherland's law to calculate the dynamic viscosity, where you can give it some constants for Sutherland's law, and it'll use those to calculate dynamic viscosity depending on temperature. You could tell it, use the Chapman-Enskog equation, which I'm not actually personally familiar with, but you notice that it gives you some other properties to mess around with that it will use to calculate, presumably, dynamic viscosity. You could tell it that it obeys the power law. Again, give it some constants. It can use those to calculate dynamic viscosity. Usually, either the power law, Sutherland's law, or constant is acceptable. Remember, for gases specifically, dynamic viscosity doesn't have a very. It has a dependence on temperature, but it's not a very strong dependence. It tends to only change noticeably if you have significant swings in temperature on the order of more than probably 20 or 30 degrees Celsius, depending on how accurate you want to be. So if you have large temperature swings, you might need to change that for gases. If you have relatively small temperature swings or no temperature change, then you can just leave dynamic viscosity as constant for whatever temperature you're modeling. Molecular weight, well, it's air. Its molecular weight isn't changing. Specific heat can change potentially. You can have it change this on based on gas kinematics, or you could leave it a constant value. Thermal conductivity, ditto. You can use Sutherland's law. You can use the power law. You can use other things to let thermal conductivity change. If you know that there's going to be, for example, large temperature swings that change the properties of air to some extent, to a noticeable extent. Let's see here. Turbulent Prandtl number. You can either define it as a constant or you can let it vary over space in terms of a field function. Field functions are a more advanced topic. We're probably not going to get to them in this class. But if you need to modify the properties of air because you're going to a sort of scenario that is significantly departed from standard kind of everyday air conditions, you might need to change some of these properties. Or you might need to change it so it's not air at all. Again, you can go into the material database and add your own or change the properties of an existing gas or select the properties for another existing gas. You have some other properties for all of these. Usually you won't need to mess with these, but sometimes you might. For example, let's see here. What are some of the ones that might actually be more useful? This you probably won't need to modify at all. If it says expert, you're usually only looking at that if you really know what you're doing. Ideal gas, let's see here. Reynolds average, Navier-Stokes doesn't have any segregated flow. You can tell it to use a first, second, or third order convective equation for segregated flow. Ditto for segregated fluid temperature. You get some more advanced options for the SST K omega solver. Let's see here. Anything else that might pop up that you want to change? That's pretty much it. So really, you're probably only going to need to change the gas properties here. What you're much more likely to need to change is some of these reference values. Depending on your coordinate system, gravity may or may not be down. In this case, this is assuming a two-dimensional coordinate system, or gravity if we have y up and down, or y is vertically up, x is to the right. It's assuming that negative y is the direction that gravity is pulling everything. You can see gravity is pulling it 0 in the x direction and negative 9.81 in the y direction. That's usually an okay assumption, but in some unique coordinate systems, that might be different. You might need to change the direction of gravity. In 3 dimensions, it'll assume that negative z is down. Reference altitude, you normally don't need to change. But if you know, for example, that you're specifically modeling a plane at 10,000 feet, you might want to plug in and say, hey, we are 10,000 feet up, so positive y, 10,000 feet. There's some maximum and minimum values here, which I will get to in a second. But if you're modeling gravity, one thing that you probably must change is the reference density. Because reference density, and this is important, has a default value of 1 kilogram per cubic meter. Exactly 1. To the observant among you, you might notice that is significantly lower than the standard sea level pressure of approximately 1, or density, excuse me, of approximately 1.2. This is a problem I ran into once upon a time when I was trying to simulate a simulation with that was basically cooling off some electronics, and the simulation swore up and down that hot air was falling. Just pure natural convection, hot air was falling. Well, turns out it's because that I was trying to do a sea level test with a reference density of 1, when the reference density really should have been much closer to about 1.16-ish, maybe 1.12 because it was kind of hot air. But the reference density should be set to whatever the free stream conditions around your system are. If you expect the air density, for example, approaching your aircraft to be 0.8, and you're trying to model gravity, you should set your reference density to 0.8. If you're doing something at sea level, it's probably approximately 1.18, 1.20, somewhere in that neighborhood. These minimum and maximum values are a thing because what STAR-CCM will do is it's going to kind of assume that if you go too far out of regular bounds of pressure or temperature, that something's gone wrong. So what it does is it says, hey, if I get a, in this case, temperature less than this maximum allowable, or sorry, if I get a temperature greater than this maximum allowable temperature, like it does its math and it says, hey, the temperature here is 6,000 Kelvin. It's going to say, no, that's not right. I'm going to, instead of letting this be 6,000 Kelvin, I'm going to make this 5,000 Kelvin. It will take that temperature and set it to the maximum value. The maximum value is pretty gosh darn generous. You usually won't need to change these. It also has a minimum. If the temperature falls below 100 Kelvin, STAR-CCM Plus is going to go, hey, that's probably not right. I'm going to set this temperature, instead of letting it be less than 100 Kelvin, I'm going to set it to 100 Kelvin. It won't let temperature go above the max or below the minimum. It will enforce these limits. It has similar limits for pressure, up and down. It also has a limit for wall distance. If it calculates, hey, and it says this cell is so thin, it's so close to the wall, it's going to let the minimum value of that be this, what is that? Not 1 millimeter, 1 micrometer. So it's going to do the same thing. It's going to not let your wall distance be less than this 1.0 times 10 to the negative 6 meters. I hope you're still awake, because I left in these reference values, I left arguably the most important thing for last. That is reference pressure. Unless it has the word absolute attached to it, every single pressure in STAR-CCM is measured relative to this value. Let me say that again. Unless it has the word absolute in front of it, every pressure in STAR-CCM is measured with respect to this reference pressure. If you see STAR-CCM say that pressure is 1,000 pascals, that actually means pressure is 102,325 pascals. If it says pressure is negative 1,000, that means the pressure is 100,325 pascals with this reference value. That is important. Remember that. If you're changing what reference pressure you're operating at, maybe you're operating at 10,000 feet, and you want your reference pressure to be the standard pressure at 10,000 feet altitude, you should change this reference pressure. Maybe you do want everything to be relative to sea level pressure always, in which case you can leave it alone. But if you want to change the relative pressure reference, change this value. Also, under physics is initial conditions, where you define where the simulation starts. Because it has to have some idea of what values to use when you start the simulation. That's these values. It will assume a pressure of 0. Now, what did we just say? That doesn't mean there's actually no pressure. That means the pressure is exactly the reference value. So in this case, if we initialize a simulation with this condition, it would have a pressure of an absolute pressure of 101,325 pascals. It will initialize it to some temperature, in this case 300 Kelvin by default. It will initialize it to some velocity, 0 by default. It will give it some parameters for viscosity by default, or viscosity and turbulence by default. Usually the turbulence values are fine by default. You might want to update the velocity. You might need to update the temperature. You might need to update the pressure. It depends what you're doing. If you have trouble getting the simulation to be stable, having a velocity, an initial velocity, can make the simulation converge faster. If you know your velocity is going to be close to 100 miles an hour, for example, you can initialize it to 100 miles an hour, and it might converge faster. You might get a result sooner. But it might make the simulation less stable. It might make it more prone to crashing on you. It depends on your setup. So, if you're having problems, leave velocity initialized to 0. But if your simulation looks like it's very stable and running great, which we haven't really talked about what that means yet, but you'll see it in the future. If it looks like it's running well from the get-go, you might be able to initialize it to some velocity that's closer to the value you expect to see. Maybe not exactly the value you expect to see, but closer to it. And that might help you get results a little bit sooner. It is possible to have more than one physics continuum. Maybe in the same simulation, you're modeling a liquid and a gas, and it's contained in solid pipes that you need to know, for example, how does temperature change through these pipes? Maybe there's a pipe that has very hot liquid on the inside and is cooled by air on the outside. Well, to know how much temperature is flowing through that pipe, you might need to explicitly model it. So you might have more than one physics node. Let's just call this one air because it's modeling air. Let's select another one for steady two-dimensional flow of water, which is effectively constant density. Rename this to water. I do recommend renaming everything, by the way. It'll make your life easier later. By default, it'll assume water when you're talking about a liquid. And maybe it's flowing in a solid pipe that we need to model physically. Well, we can select two-dimensional, steady, solid, and what else? And we want to know how temperature changes in this solid, so we select segregated solid energy. The solid is constant density. And we get another node that is going to be our, I'm going to say, aluminum pipe. Notice it has a different icon to show that this is a solid. And by default, we selected solid. It assumes it's made of aluminum. Pure aluminum. So you can model multiple different types of physics inside of one simulation. Because if air is interacting with water, is interacting with aluminum in some way, that might matter, and you might need to model the separate things. So that's kind of a crash course in the continua. I'm going to release another video shortly that talks a little bit about how do we go from geometry, where we talked about making some basic parts, and actually telling it what we want to model. That'll be in a future video.